Happy Tuesday, everyone. So in this video, we're going to be talking about embeddings. So embeddings are a really cool topic. So big picture is embeddings represent data as points in a space where locations are semantically meaningful. So just as a small example, if you have two sentences like Michael Jordan is the greatest player of all time and Kobe Bryant is one of the best players of all time, those sentences should be very close in space compared to a sentence like the most popular color is green. That should be farther apart from those two. So that's the idea of embeddings. So why are they so popular these days is especially in their use of in RAG. RAG is Retrieval-Augmented Generation, which basically puts LLMs on a new level, like on steroids, basically. So it enhances the accuracy and reliability of LLMs. Basically, LLMs are only trained up until a certain point. They only know what they're trained, basically. They don't extrapolate too much to real-time news events and real-world future updates. So what RAGs do is they add those knowledge bases, like news data or databases or whatever, and the LLMs can now incorporate that information to give users accurate responses and up-to-date responses. And there are futuristic stuff like there's agents that can reason and that sort of thing. We'll talk about that in the next videos. Okay, but embeddings are a key part of this RAG system, and I'll explain that in a second. The other two things we're going to do in this video is we're going to show you how to visualize embeddings in 2 dimensions with principal component analysis. There's also a TSNE, but PCE is a little bit simpler to do. And then just for the sake of completeness, we're going to show you how to create a sentiment analysis classifier with these embeddings and compare it to a dumb, naive baseline. This is the same sentiment analysis dataset from Alpha Vantage I've used in my other videos. So yeah, let's get started. So first of all, there's many embedding models, many competing models. OpenAI, of course, has a model. Google has a model and all that stuff. In this tutorial, we're going to use 2 models. We're going to use there's a leaderboard on Hugging Face. So if you go to this leaderboard thing, you'll see the #1 model is voyage.ai. Once this loads. So voyage large to instruct. This is the embedding we're going to use. It's the #1 one. And soon they're going to have a finance specific one, which is very exciting. Okay. And okay, so we're going to use that. And then we're going to also use embeddings from OpenAI for the text classification part. Just because like maybe some of the rate limits for this voyage are not enough for the text classification part. The RAG also needs LLM, and for that we're going to be using OpenAI like GPT-4 or some version of it. And yeah, so let's get started. By the way, in the future I'll talk about Google's Gemini more in the context of Vertex AI. So first let me describe embeddings in big picture. And let's dive in. Okay. So, so what are embeddings? So basically, sentence and document embeddings are vector representations of text that capture semantic meaning, and they enable comparison and analysis of linguistic context. So semantics is a fancy word for saying meaning in language. So the pairwise distance of similar documents or sentences is smaller. So for example, in our world, Judge nixes Elon's compensation package. Elon Musk loses $56 billion should be more similar to each other than Meta to release Llama 3. And these embeddings are critical in the aforementioned RAG because they optimize the LLMs, of course, by retrieving this external content, this external like news articles or tweets or let's say actual data, but they need to get these knowledge bases in a way that's possible. And embeddings help search that space to get the best matches between queries and documents. So like if we're saying like what is the biggest what is the biggest risk to Tesla? And then the RAG would search over all the documents, all the news, and basically can spit out the biggest risk to Tesla is that Elon Musk's compensation package is not approved, and Elon Musk will leave Tesla, and Tesla AI will go out of Tesla, for example. So the embedding part is a way to find documents similar to the query, right? It's a way to like find like the smallest distance between the documents in the query. By the way, these embedding vectors are like, let's say 754 dimensions, and so the query is 754 dimension and the document is 754 dimension. So we use usually cosine similarity, which measures the cosine of the angle between those two vectors as the metric for similarity. Okay, so just to show you guys like, oh, oops, sorry, there you guys see my full computer. To show you guys kind of the a typical RAG pipeline, and this is from voyage.ai. Let me make it a little smaller. So basically what happens is you have this corpus of documents. These are all like, let's say, news articles or tweets or whatever. You have it, you throw it in an embedding model, and now you have documents and embeddings. And then you have a query. And the query is also fed into an embedding model. And then basically here, what you do is you do some cosine similarity. You find like documents that are similar, let's say a list of candidate documents that are similar, like the most relevant documents to your query, and you retrieve those documents, and then you use like a generative AI model, like GPT-4, for example, to basically synthesize this information, put it together, and get a response. So that's basically the big picture, what it does. So this is not that important, especially if you guys can skip this part, but a little bit of technical things. So how are sentence embeddings computed? So there used to be like a method, very popular would be, we had word embeddings like word to vec, glove, and that sort of thing, where like basically things like cat and dog would have basically similar vectors compared to like something unrelated to them. But this wasn't, and then what you would do to get like a sentence embedding, this was like the old method, you would take like an average of these individual word embeddings. But it wasn't so great because order really matters. Like if you switch the order of a few words in a sentence, it can make a complete difference in everything. So let's say you can have two sentences and the word stock can be either a piece of a company or inventory. And depending on the sentence and the context of the surrounding words, you can have such different meanings. So now there's a modern method where we use transformer neural networks to learn context-aware representations of each word. And then we take an average of these context-aware representations. And so how are these sentence embeddings learned? So it's kind of similar to the LLM training. What you do is you pre-train a large amount of unlabeled text data from the internet or other sources. So you get this like pre-trained model. And then you find a data set of similar sentences and you tune the neural network to move the embeddings of similar sentences together and dissimilar sentences apart. So let's say you're doing Q&A. You would want the question and answer to be similar, and then you can have dissimilar pairs be just two random selected sentences. And you can basically do a contrast, like you predict if it's similar or not. And just a little extra note is embeddings are computed for each subword or token byte level as opposed to word level. This is the modern version. So what's good about this is like you can learn novel words, like words that are similar to each other but like maybe off by like a little stem or whatever. And it's good for misspelled words. So people like me misspell everything. So it's great. Okay. So you can measure performance by how it does in things like semantic similarity, sentence classification, question answering. Let's not get into too much details. Maybe just real quick, some other applications of embeddings can be classification, clustering, outlier detection, semantic search, and recommendations. We'll show the classification in this case. So, okay, so finally, let's get started. I guess I spoke too much. So first, we need our installs. Let's install. We're going to use this Voyage AI. And Voyage AI is actually really cool. And we're going to need OpenAI. So while these are installing, let me just talk about the packages we'll use. So we're going to need like Keras and Pandas and NumPy for everything, but Keras for neural network classification model. We're going to need that later. And then we're going to need, you're going to have API keys, so you need this user data from Google Colab. And I'll show you how to use that in a second. We'll have a few plotting libraries, PCA for visualizing embeddings. sklearn has this cosine similarity function for measuring similarity between two embedding vectors. And then we're gonna have metrics and the naive Bayes we're comparing against. We need also Voyage AI and OpenAI's packages. So okay, this installed. Okay, so I'm gonna import everything. Okay, so now you can get you need an API key for Voyage AI. So you can go to the link here. And Voyage AI is really cool. They're like the #1 query thing. So you have to log in again. It's always annoying when you log in. Sometimes I like sign out because I don't want all this personal information, and then I log in. So then you have these API keys here. You can generate a new key and stuff like that. Voyage AI is really cool. I highly recommend it, and soon they'll have a finance thing. Okay, so you get your API key here, and this user data.get Voyage API key. What happens is you get your API key here, and in Google Colab you put it in your secret, and you do paste here, and then you make sure it's available, and this keeps all your secret keys. So now you can just do .get Voyage API key, and you're connected, right? Okay, so now. Let's show you guys this amazing thing in action. So let's say we have a list of documents, and these are just random headlines I took. So Tesla bull, Gary Black says likely approval of Elon Musk's 56 billion pay package, and I have things like NVIDIA launches 9 Grace Hopper powered supercomputers. So these are some random finance articles from, say, Tesla, NVIDIA, Rivian, Alibaba, I think also. So just some random articles. I didn't choose Microsoft, but for some reason, I guess Microsoft has a few things. Looks like I have actually a duplicate, so let me get rid of that. Okay. So these are the documents, right? So I take the documents, and now like we want to, I'll show you how to vectorize and embed these documents with Voyage AI. So you can call this function vo.embed. So I do document embeddings equals vo.embed documents model. They have a lot of models, but their strongest one is Voyage large to instruct, and input type is document.embeddings. There's also input type is query, and you should use query for the query embeddings. Let me just write for document, use input type equals document. For query, use input type equals query. And they have many models. This Voyage to instruct is the best one. Okay, so now we have the document embeddings. Did I click it? I didn't realize that. And the document embeddings. Okay, so how do these embeddings look? So for each document, how many documents did we have? We had basically we had 30 documents. I thought we had less, but okay. We have document embeddings. It's going to be a list of size 30 also. And each element in this list we'll have document embeddings 0. We'll have a vector, and this vector would be dot shape. Is it a list or a shape? List has no object shape. Okay, so it's a list of lists. So it'll be length list. So each will have the embeddings are dimension 1024. So, okay, so each of these are 1024 dimensional vectors. Okay, so now let's show you an example of a minimal retrieval system. So the minimal retrieval system is, okay, you have some sort of query and you want to find the documents, let's say K documents most similar to the query, right? So let me show you how to do that. So first we need to define a query. So let's do something like query equals what is the status of Elon's 2018 compensation plan. And it would be interesting to try if you wrote comp plan, if that was good enough. But let's write comp plan just to see if this is actually good. Okay, so now what we have to do is, now that we have the query, we have to get the embedding of the query. So it's similar to what we did above, except we need input type equals query. Look, input type is query. Let me just write it again because it's important. Input type equals query. Oh, and make sure you use same model. If you use different model, it gives bad results. I made that mistake. I accidentally used voyage something else and I got bad results. So now you get this query embedding, right? Okay, so now we want to find, like, let's say the K similar documents to this query, right? So we're going to do this K nearest neighbors with the distance as cosine similarity, or the similarity score as cosine similarity. And this is going to return the top K most related embeddings with their corresponding indices, this function. So let me show you guys what it returns. So let's call it with K equals 5. So the retrieved embeddings are going to just be, isn't that cool that now Google COLAB has this like AI thing? So these are the retrieved embeddings. This is the list of lists. And then the retrieved emb index. This is the index of the top documents. Okay. So let's see, I already think that the comp thing kind of messed things up, but let's see what it gives us. Let's look at how it looks. So let's say we can do, we can do, okay, sorry. So what we can do is we can get the documents from the index. So documents index for index and retrieved embedding index. And then we'll print the documents in order of the most relevant. So actually it is good. Tesla's board credibility at stake with 56 billion Elon package, says Ross Gerber. Super grateful for Tesla as an investment. Creighton Research, Elon deserves 47 bill. Tesla bull Gary Black, 56 billion, likely approved. So this is really good. This is amazing. And this is just with the cosine similarity. It's kind of amazing how like good it is. It's close to like our query, which was like, what is the status of Elon's comp plan? We didn't even write compensation. We wrote comp. So that's pretty cool. So now I want to say like there's one further step that people do. And this is for optimization is like, we found the K most similar things with this K nearest neighbors. And so we have these, what's called initial retrieve documents. So these are candidates. And it was like kind of using like a simple thing like cosine similarity. But now there's something called the re-ranker, which you have these set of 5 documents and you re-rank them with like a much more sophisticated model, much more sophisticated neural network model that will re-rank these and find even the most relevant things with semantics. And now once you re-rank that, you throw it into the like generative model like GPT-4 and you get the response. So let me show you guys how to do that. And what confused me earlier was I was like, what is the difference between this re-ranker and this first pass of finding the most similar documents to the query? So the first path is just to be fast, kind of take a few of the best ones, but don't worry too much about accuracy. And the second one, and like do it fast. The second one is a lot slower, worry about crazy accuracy. So now what we had is we took the top 5 documents here, and with the re-ranker, let's take, say, the top 3, right? So we do VO again from the voyage, and we put the query of the retrieved documents, and we use this re-rank light 1 model to get the top 3. Okay, now let me just show you guys the top 3 re-ranked ones. Although all the ones on top seem relevant, I do think Gary Black is the most relevant, since all these talk about the pay package, but this is credibility at stake, and this is like deserves this package. These are like opinions, right? But here he's talking about the status. Gary Black says likely approval of Elon's 56 billion pay package. If only we could, in a perfect world, scrape Twitter. Twitter's API costs so much money since Elon took over, but like we can get like if Gary Black's tweets and some of these really good analysts. That would be really good for these RAG models, but Elon made it expensive. Okay, so now let me just, for the sake of completeness, show you a complete RAG model. So this is where like we merge this retrieval element with a generative model. So we're gonna use OpenAI for this. So remember, like you can go to this like OpenAI and get your keys, add a key, whatever, create new secret key, add it, whatever. You have to make an account, but then you put the secret key here, as before we said, OpenAI key. I talk about this at length in my other videos. So now we load our API key using the user data thing. And let's initialize the OpenAI client. Okay, so now let's take the retrieved document. Actually, I retrieved 3 documents here. So let's actually take just the top one. And let's use it as a prompt for our text generation model. So let me show you quickly how that's done. So prompt would be based on the information. Retrieve docs, the top one is 0. Generate a response of query. Okay, so let's see what it gives us. It kind of gives us like the way the chatbot will talk to us. See, as of my last update, Elon's compensation plan, which was approved by Tesla's board of directors, shareholders in 2008, was an unprecedented package largely based on performance of the company. And it talks about like the history of the plan. And then this worked before. I don't know what I changed that made it not work. So let's try to figure out together. Retrieve docs. What was our retrieve? This didn't work as I expected for some reason. Doc 0, because we want this information, credibility at stake. Okay, that's bad. We wanted these ones. We wanted documents re-ranked. I think that's better. Documents re-ranked. Dot results. Let's do 0 and then do document. Okay, so I think this is a better thing. I don't know if this will fix it, but like, okay. Yeah, what messed up here? Maybe it's because I have this weird. Okay, this is a better response. It says, based on the information provided, it appears that Gary Black, known for his bullish stance on Tesla, although people on Twitter sometimes say he's bearish, suggests that the likely approval of Elon Musk's compensation plan is expected to be a significant positive event for the company. However, the statement provided does not indicate the current status of Elon's 2018 plan. And then it talks about like big picture things with plans. Let's not talk too much. We'll talk about this a lot more in other videos. So now I just want to show you a cool visualization of embeddings. So you can use TS&E in things way more sophisticated, but like you can also do like a simple PCE and you can get some embeddings. PC, of course, is a dimensionality reduction technique, which basically gives you like dimensions that are like like each component represents are linearly independent. They represent like a big variation of the most variation of your data. So you can do this PCA model where you do like let's say num components is 2. This is from sklearn. You fit it to the document embeddings, and then you transform it to get like new values in the 2-dimensional space. So now we can visualize this with Plotly. So what I did is I created a data frame here with this new values because it's just a what's it called? It's just a NumPy array, NumPy matrix. So I set the columns to X and Y for the XY coordinates, and then I added the text column to be the text of the documents, and then I did a scatter plot and look at what we get. So it doesn't mean anything, but like because I wrote hover name equals text. When you hover, you see here you see Tesla board credibility at stake with 56 billion Elon. Tesla aims to cut 400 jobs. We recently undertook cost cutting. So you see like these are Tesla related stuff. Cost cutting, Elon package, Tesla HR leaving the company, Elon Tesla. You go here, you see Meta's estimate, Meta's beat. Rosenblatt maintains buy Meta, Bernstein Meta, Amazon. I don't know how it's close to Meta, but this is a 2-dimensional thing. Apple here, Alibaba related things here, I guess. This is like Alibaba. China and Alibaba, I guess, have some similarity. Microsoft. So, I mean, did a good job with Tesla, but with other stuff, it might do less of a good job. Maybe it's because we had these are NVIDIA related things. So see, like this embedding does a good job out of the box, and we didn't give it that much examples. We gave it like 20, and they were very short sentences and were very bad. So anyways, so that's really cool, I think. And anyways, okay, so now let me show you guys like another application. So you can actually use these embeddings for clustering or classification. So let's do sentiment analysis classification, because in my other videos on like fine-tuning LLMs with Burr and also Llama 2 and using Llama 3, sorry, and using Llama 3, and I did text classification, and so we kind of want to have results and we can compare it to that. So let's show you how to do that. So just a reminder, I have this YouTube a video of how to get this labeled Tesla sentiment data from Alpha Vantage. So let's load it and get started. So remember, once you get this data set, you can load it here. You basically put, I already put it, but like you basically upload the file, you click Tesla sentiment new, it loads, you wait a second until it finishes loading. Okay, and then once you do that, you read the data from CSV. I already did this part, and I don't want to run it again, and I'll explain why in a second. Basically, you also have labels as bearish, bullish, or neutral. So that's why I do as type category. It moves it from string to category, and then you do cat.codes. This will give you like a 0, 1, 2 representation. So we're gonna use that. And then I'm gonna just have this map. I guess it's funny, the AI wanted to give me the map here, which is cool. But like I did it myself. I did display labels equals I to L for I, L, and enumerate df label dot cat categories. This gives me like a labeling from it basically gives me a labeling from the integer index, like 0 to negative 1 to neutral 1 sorry, 0 to negative 1 to neutral, 2 to positive, something like that. So that's what this display labels thing does. Okay, so now let's we're gonna be using the summary column. So just to remind you guys, this data frame had a summary and had a headline. The summary column, this is the one we want to do the embeddings on for this video. Of course, in real life, you probably want to add the headline, and if you have the full text, that's even better. But let's just use a summary for now for simplicity. So here we're going to use the ADA embeddings. The Voyage AI embeddings seem more interesting, but the thing is, like, there's some rate limits and that sort of thing. So like I have an OpenAI account and I pay for it, so this should handle some of the rate limit issues. So let me show you guys how that's done. So we have this get embeddings function, and this get embeddings function, what it's going to do, and this is from OpenAI's documentation. I guess it gets rid of new lines, but we don't really need that. But like it returns client.embeddings.create and input. You put as input your text here, or I guess you can have a list of text. But anyway, sorry, you can have a list of text in one thing, and then you put your model, and then you take the embedding like this. So big picture is just copy this code. This is what OpenAI gave. The most important thing is this is their embedding model. You can also have a large version that might be better, but let's use a small version because it's, I guess, cheaper and easier. So you have this get embeddings thing. And then you use pandas apply to get the embeddings. So I call it ADA embeddings because that was what it was called. And you do summary.apply. So you apply to each summary element in the data frame. You apply this get embeddings function. And then so you get the embeddings. And let me show you guys kind of how the embeddings should look like after you run this. This does take some time. That's why I did it before I presented this video. So if I do this embeddings, you see each of them is a list of dimension of a certain dimension. So let's actually show you what it is. df ada embedding .iloc 0, and then let's do length of that. So let's see the embedding dimension. I think it's 1536. So it's crazy. The Voyage AI is less dimensions, and it's really good. And soon they're gonna have a finance one, so that's interesting. And by the way, let's say you did this hard work, you waited a long time. You probably want to save your embeddings. So it costs money to generate embeddings, and B, it takes a lot of time. So you should really save it to like a database and that sort of thing. But like for now, we can save it to a CSV file. I wrote index is false. And then let's say we already have it saved. We can reload it like this. We can reload it. But then because when you read it, this becomes like a string column, the ADA embedding column. So you can do this like .apply eval and then .apply np.array. That will give you the ADA embedding in the right format. So that is important. Okay, so now let's show you the text classification for sentiment analysis example. So like my other videos, I split the data set into the first 60% train, let's say the first 60% in time train, next 20 val, last 20 test. This is much better than randomly shuffling and doing like 60-20-20 split, because then documents similar to each other, like Gary Black thinks thing will be approved, and Gary Black Tesla Bull Gary Black thinks it will be approved, won't be in both the train and test set. But of course, things like on the border here can have minor leakage, but this is pretty trivial in this case. Anyways, I talked about this at more depth in my other video, so I split it. The train set now is 3,000, and the val and test have about 1,000 each. So let me just show you a simple I guess I don't know how to spell multi-layer perceptron neural network. So the inputs are going to be this 1,536 dimension embeddings for each document, and the output will be bearish, bullish, or neutral. So first, let's get it in the format needed for Keras. So that's we need to separate basically the X and Y components. And we need to do that for the train, validation, and test set. So here, the target, I just take out the target. Remember, the target was the integer encoded thing. And then also I do this np.stack of these lists for df.train embedding. This will give me xtrain in the right format. So let me just show you guys what it does. And you do the same for val and test, but xtrain now looks like this. It's now basically a numpy array. That's what this thing does. It stacks the lists together, and it'll give you like a numpy array or numpy vector of this shape. Okay, so now this is not a video on Keras. If enough people are interested, I'll make a Keras video soon. My kids just walked in. But okay, so like let's say let's find a neural network with hyperparameters in Keras. Keras, of course, is like the simplest way to do neural networks and deep learning. It's kind of like almost like sklearn's .fit.transform type thing, or .fit.predict. So you define the model. I do Keras.sequential. First layer is 32 layer dense. Then I have a dropout, which randomly drops out 20% of the nodes, so it isn't reliant on specific nodes. That helps prevent overfitting. And then the last layer is dense 3, because there's bearish, bullish, or neutral labels, and sigmoid because we want a prediction. So now, just a few more details. We compile the model with a loss function. Sparse categorical cross entropy. That's like for multi-class classification. We give it an optimizer. Atom is the most popular, most modern, and then a metric is accuracy, and then a callback means we do early stopping if the validation accuracy after, let's say, 3 steps doesn't improve. That's like for the overfitting part. So this is not a course on Keras, so let's just run it and see how it works. There's also a number of epochs, that's number of passes through the data, and the batch has a 32. And I should have shuffled the training set. Might have given me a little bit better results. You know what? Should I do that? Forget it for now. Shuffling the training set is probably the best practice to do. So anyways, as you see, the training loss will always go down pretty much, and the validation loss will go down and then starts going up once you're overfitting. Same with the validation accuracy. It goes up to 60%, and then it goes down when you're overfitting. And let me just show you this in a plot. So I added this plot history thing. So as you see, like, this is training, the loss is always going down, and the validation loss goes down after a few epochs and then starts going up because you're overfitting. Accuracy similarly goes up and then goes down after a few, but for train it always goes up. Okay, so now just to get let's just get predictions on the test set, and then I'll show you how to evaluate the model and get like all these metrics like the confusion matrix. So you do model.predict, and then let me actually split this into 2 steps for you guys. So if I do model.predict, I get number of documents by 3, and then I do argmax axis equal 1 to get the prediction from the probabilities. So that's my y hat. My kids are here crying a little bit. So let's evaluate the model. Let's just use a few metrics we used in other videos. So like I did accuracy is 53%, balance accuracy is 51%, and then I have like precision recall and that sort of thing, F1 score. And then we can do the confusion matrix by using sklearn's confusion matrix. And you get something like this. And let's display the confusion matrix in a pretty way. So this is the number of times it's actually negative that we predict negative. And then this is the number of times it's neutral that we predict negative. So this is like wrong. So these are the right ones, and all the other ones are wrong. As you see, I would say we do a very good job at the neutral. I guess we do a good job at the neutral. The negative not as much. The positive is pretty good. I think this is slightly worse than the fine tuning for text classification with COLAB we did earlier with Llama 3, but just to give you an idea what you can do out of the box. Okay, so one more thing is I wanted to compare this to naive Bayes. So naive Bayes is like the first text classification model we learned for spam, no spam in any class. Accuracy, balance accuracy is way worse. Precision, recall, all that stuff. Look, it was 0.45, 0.58, and 0.52. This is way smaller here. And look, it's only 18 here. It's 273 here. I don't know. I guess confusion matrix are weird because like it actually does a good job in label 2. So you know what? Sometimes it's good to combine models, but the accuracy is a lot worse. Naive Bayes, just to remind you guys, it's kind of like a model that assumes like words are conditionally independent and like you have basically like a big product between words, that sort of thing. This is not a class in NLP. If you're interested in this, I will be happy to make a video eventually. And here are some really good resources. So let's start first of all with the Voyage API. So they have a quick start tutorial that explains things. Actually, a lot of my things are similar to this, which is really good. The Voyage AI documentation is great. And then this is an amazing resource from Andrew Ng's deeplearning.ai. You have all these courses and that sort of thing. So there's actually these short courses, and there's one on embeddings. I went halfway through the course. That's where I got the idea for the PCA visualization, to be honest with you, although my graph is different than theirs. They use matplotlib, I use plotly, but like there's like tons of things, vector databases, understand and apply text embeddings. This is the one that's related. And then there's also cool things, fine-tune large language models. Interesting things. It's a good resource. Anyways, hope you enjoyed this video. If you're new, please like and subscribe. Add me on Twitter, comment. Thank you so much.